Hey everyone, welcome back. Today's our topic of discussion is geometric mean. A value that represents the entire data set is called as the central value, and the measures that can be used to find such central value are called as measures of central tendency. And different measures of central tendency are especially arithmetic mean, median, mode, geometric mean and harmonic mean. In our channel, we have already discussed about arithmetic mean, median and mode. Whoever want to refer can please go and refer the videos in our channel. Today, we are going to discuss about geometric mean. Where is geometric mean used? Geometric mean is generally used in situations where the data set exhibits an exponential growth or decay. That is, the data keeps on increasing or decreasing in an exponential format or in powers instead of the linear format. In such situations, we go for geometric mean. There are many examples where geometric mean is used, especially in calculation of the rates of interest, in calculation of the population growth in a particular area or a country. Since we have seen in which situations geometric mean is observed, we'll see how geometric mean is applied to the given data. Initially, let us suppose that there are n variables x1, x2, so on, xn. Then the geometric mean for such data can be given as the nth root of x1 into x2 into so on xn. But we know nth root is nothing but power 1 by n. So I can write geometric mean is equal to x1, x2, so on xn whole power 1 by n. Now I can apply logarithms on both sides to give log geometric mean is equal to 1 by n log of x1 plus x2 plus so on xn. Once we have applied, here we have got plus symbols. Now, which is nothing but 1 by n, summation of all these values can be represented in terms of sigma, that is 1 by n sigma log xi. Finally, this is log gm value. So, gm value will be anti-log of sigma log xi by small n. This is my basic formula for geometric mean. Now, we'll see how the geometric mean formula varies in terms of individual, discrete and continuous series with examples. Let us consider this data for our geometric mean calculation in terms of individual series. Here we have the x values as 180, 190, 240, 386, 492 and 662. As our formula demands for log xi, we find logarithm of each values using our scientific calculators. Log of 180 is 2.2553, log of 190 is 2.2788, so on. Log 662 is equal to 2.8209. Now, substituting in this formula, we have sigma log xi. That is, we need to add all the values in this column, which gives us sigma log x is equal to 15.0138. On substitution, we get anti-log of 15.0138 divided by 6, where 6 in case of individual series is nothing but number of values. The number of x values here is 6. So on substitution, we have anti-log of 2.5023, and using the scientific calculator, we can find out the anti-log of this value. So for this given data, the geometric mean is given by 317.9. Now let us see the formula for geometric mean in terms of discrete series. In individual series, we don't have frequencies of each values. So the formula will be x1 into x2 into so on xn whole power 1 by n, the nth root of product of individual numbers. But whereas in case of discrete series, we have frequencies of each number. So the formula will be nth root of each x value raised to its frequency power. That is nth root of x1 power f1 into x2 power f2 so on xn power fn, which is nothing but x1 power f1 into x2 power f2 so on xn power fn whole power 1 by n. Applying logs on both sides, log geometric mean is equal to 1 by n fi log x1 f1 1 by n f1 log x1 plus f2 log x2 plus so on plus fn log xn, but addition represents sigma. So we take 1 by capital N. Sigma I runs from 1 to small n, fi log xi. Here n is number of values in the data set. Here small n is number of values in the data set that runs from 1 to small n, and capital N will be our sigma fi. So finally geometric mean is equal to anti-log of sigma I runs from 1 to small n fi log xi by capital N. Using this formula, let us see how geometric mean is calculated in terms of discrete series. Let us consider this example for our discrete series in finding geometric mean. We have x values as 14, 36, 45, 70 and 105. Frequencies as 2 for 14, 5 for 36, 1 for 45, 3 for 70 and 12 for 105. Sigma fi is equal to our capital N value that gives you 25. As the formula demands, first we need to find out log xi. So I take log 14 value to give 1.1461, log 36 value to give 1.5563, so on, log 105 value to be 2.0211. In terms of individual series, we need only sigma log xi. So I have added all the values of log xi. But here we require sigma fi log xi. So I need to multiply each log x with its respective frequencies. That is 1.1461 into 2 to give 2.2922. Similarly, 2.0211 to be multiplied with 12 to give 24.2532. So I need to add all these values in this column to give sigma fi log xi. The value is 41.5151. Substituting all the values, we see anti-log of 41.5151 divided by 25. So finally I get anti-log of 1.805, and finding out the anti-log value in scientific calculator, we get the geometric mean value as 63.82655. Now let us see how the geometric mean is calculated in continuous series. Now let us see for continuous series. Similar to that of discrete series, continuous series also have the same formula, because in continuous series also we have the frequencies. The only difference between the discrete and continuous series is that the data set given to us in case of continuous series is in terms of class intervals, while in case of discrete series we have x values directly. Since the data is given in terms of class intervals, first we find the midpoints of each class interval to give the x values and use the same formula of discrete series for continuous series also to find the geometric mean. Now let us consider the data of class intervals for continuous series. We have to find out the geometric mean. We have totally been given 9 class intervals. These class intervals need to be converted into midpoints in terms of x. Lower interval plus upper interval divided by 2 will give us the midpoints. That is 4 plus 8 by 2, that is 12 by 2, midpoint is 6. So we find all the midpoints. We have the respective frequencies. As the formula demands, we first find out log x for each x value. Log 6, 0.7782, log 10, 1, log 14, 1.461, so on. After calculation of log x values, we need to multiply the respective frequencies with each log x. So I multiply 6 with 0.7782 to give 4.6692. 10 with 1 to give value 10. 18 with 1.461 to give value 20.6298, so on. Now we need to add this complete column to give sigma f log x to give the value 137.1936. Also, capital N value is sigma fi, which gives the value capital N is equal to 109. Substituting the values, we get geometric mean is equal to anti-log of 1.2587 to give 18.14. Since we have seen the calculation of geometric mean in individual, discrete and continuous series, now we'll see how and why harmonic mean is used in terms of individual, discrete and continuous series. The last and final measure of central tendency is harmonic mean. Why is harmonic mean preferred even though we have 4 other measures of central tendency? Because Harmonic mean is specially required when the data is given in the form of reciprocals, inverses, or ratios. When smaller amounts of data are given higher priorities and require more weightage, for such type of data sets we require harmonic mean. Some major examples where harmonic mean is preferred will be in situations like finding out the average speed in order to cover a particular distance, but varying rates of coverage is given. Suppose the total distance is from A to C. From A to B, there is x1 rate of speed, and from B to C, there is x2 rate of speed. Then the average speed that is required to cover the distance from A to C can be found out using harmonic mean. The next example will be to find the maximum toxin level in water. To find out the different toxins that are available in the water, like arsenic, lead, and other heavy metals, we can use harmonic mean to find out. In the finances also, the average price multiples, etc., can be found out using harmonic mean. Now, since we have seen what harmonic mean is and in what situations harmonic mean can be applied, now we'll see how harmonic mean is used in individual, discrete, and continuous series. Okay, this is our data with respect to individual series. We are given 1, 2, 3, 4, 5, 5 values of x's. Okay, our formula demands for the reciprocals of the values in the data set, that is 1 by xi. So what I'll do is, I'll first find the value 1 by xi for each x to give these values. But we require sigma 1 by xi. So I need to add all the values in this column to give 0.035786. And small n value is the number of values in the data set, which is equal to 5. So I'll substitute to find n value can be taken up because 1 by n is nothing but n. So n will go to the numerator. N by sigma 1 by xi. In place of n, I substitute 5. In place of sigma 1 by xi, I'll substitute its respective value. In place of n, I substitute n. And in place of sigma 1 by xi, I'll substitute its respective value. Finally, the harmonic mean value will be 139.719. Now let us see an example for discrete series. Consider this example for discrete series. We have 5 values similar to that of our individual series 130, 135, 140, 145 and 150. Their respective frequencies are given. Now, our formula demands for sigma fi by xi. In individual series, we had sigma 1 by xi. But since this is discrete series, we have frequencies for each x value. Our formula has sigma fi by xi. So what I'll do is, in the third column, I'll find the values of fi by xi. 3 by 130 to give 0.0231, 4 by 135 to give 0.0091, so on. Now the sum of this third column, that is fi xi, is made to find sigma fi by xi, that is 0.1648. Substituting the values where capital N is equal to 26, we have harmonic mean is equal to 26 by 0.1648 to give us the value 157.7669. Similarly, we'll see an example for the continuous series data to find the harmonic mean. Let this be the example of continuous series to find the harmonic mean. As we know that in continuous series, the data will be given in terms of class intervals with their respective frequencies. To find any measure of central tendency, first of all, the class intervals need to be converted into midpoints to find out the value. Now, the class intervals totally there are 5. So, small n value will be equal to 5. The class intervals are converted into midpoints using lower limit plus upper limit by 2. That is 0 plus 10 by 2, which gives 5. 10 plus 20 by 2, which gives 15. Next is 25, next 35 and next 45. Now, we have converted all the class intervals into midpoints. We have the required frequencies. Our formula, as it demands, requires sigma fi by m, where m is the midpoint. We can write it as mi with respect to small I. So, our formula is sigma fi by mi. So, what we'll do is, we'll find out the next column fi by mi. Divide the respective frequencies with the middle points. 8 by 5 gives 1.6, 12 by 15, 0.8, 20 by 25, 0.8. Similarly, 4 by 45 to give 0.0889. We have sigma fi by mi, so I'll add all the values in this column to give 3.4589. Substituting the values where capital N is equal to sigma fi is 50, we'll have harmonic mean is equal to 50 by 3.4589 to give the value 14.4554. We have discussed what are the different situations where the different measures of central tendency are used and how the formulae are applied in individual, discrete and continuous series separately. Hope all of you have understood the different measures of central tendency, their applications and construction for the given data. Please do get back to me through comments regarding any doubts you have in this topic or in the introduction of statistics. Both of these are placed in the playlist of our channel, Doubt Free Statistics. Thank you for watching. Stay connected.